All right, so let's start on vector spaces. So a vector space is a set of objects, and we're going to call them vectors. There's two major operations, addition and scalar multiplication. So scalar is some real number. We're going to use the letter C or C and D. And we're going to be playing with vectors U, V, and W. It's going to feel very similar to what we've been doing because we've been playing with vector spaces the whole time. We just haven't used the rules to determine if something was a vector space. So if a set is a vector space, then it satisfies all 10 of these rules. So let's just kind of walk through them. So if I have two vectors that are in the space, then if I add them, it stays in the space. Doesn't matter which order that I add them. It doesn't matter which order, the grouping of them when I add them. There is a zero vector in the space so that if I add it to a vector, I get the vector itself. There is, for every u or every vector that's in the vector space, there is a negative u so that when I add those two together, I get to the zero vector. If I multiply the vector times the constant c, I stay in the vector space. I can distribute this constant c. I can add the two c's together, or I can and then multiply it times the vector, or I could distribute the c and the d to the vector. I can multiply the c times the du, or just do the cd times the vector u. And if I take 1 times the vector, I stay in the vector. So these all make a lot of sense because we really have been using things that are vector spaces, like R2. R2 is a vector space. R3 is a vector space. So vector space vectors that are in Rn, they follow the addition rules and the scalar multiplication rules. All right, so others that are vector space, other examples. So these are just examples that I just want you to understand, and we'll be kind of playing with finding things are subspaces on the next page. So the set of 2 by 2 matrices are a vector space. So if I can add them, there is a zero matrix. I can multiply by a scalar. So just kind of quickly looking over, yeah, that's how it doesn't say anything about multiplication, right? Just scalar multiplication, not multiplying of matrices, because that's a big deal. So the set of m by n matrices is a vector space. And so this is a more general case of this one. All right, so the set of real valued functions. So functions that are like 2x plus 3x squared, right, where there's real numbers here in front of, these are a vector space. So I'm not going to go into the example of that. I'm going to go into the examples with these polynomials because this is all real valued functions. So we're going to go specifically into just these kinds of polynomials, and we'll be playing with these kinds of polynomials quite a bit. So let's get used to this notation. So the degree of n has to be bigger than or equal to 0. So this is a polynomial of degree at most n. And the a's are the constants, right? So the coefficients, they're all constants, and they're in front of the real variable t. And we say the degree of p, degree of the polynomial, is the highest power, just like we do in regular algebra. All right, so we call this p of t that's equal to just the constant. We say that the degree of p is 0, right, because there's t to the 0 there. And only if all the coefficients are 0 do we say p is the 0 polynomial. So the 0 polynomial is the number 0, right? All the coefficients have to be 0. All right, so let's look to see what we'll be doing. I will not be having you go through all 10 of the items to show that it's a vector space, but what I will have you do is determine if a set is a subspace of a known vector space. So we're going to stay in an area where we know things are vector spaces already, like 2 by 2 matrices, like R3, like R2, like polynomials. So we already know these are vector spaces. So I'm going to give you criteria, and then you'll need to determine whether it's a subspace. So to show something is a subspace, you only have to show 3 criteria. If we show these 3 properties are true, then I know that this subset H is a subspace of the major vector space. All right, so the 3 things are: 1, you have to make sure there's a 0 vector. 2, that it's closed under addition. So for any time you have 2 vectors in the subspace, that when you add them, they stay in the subspace. Remember, H we're just determining is a subspace. So H, the subspace, is closed under scalar multiplication. So that means that when I multiply it by C, that is in H as well. So get used to this this wording. Closed under addition means that if I take 2 vectors in the subspace, that if I add them, I stay in the subspace. Closed under scalar multiplication means if I take something that's in the subspace and I multiply it by a constant, a real number, that stays in the subspace. So those are 2. And then the third is that there's a 0 vector. Something that acts like if I take and add on the 0, then I get back to the U itself. That's how the 0 vector operates. All right, so let's look at here. So if I have, for example, these 2 things inside this subspace, right? These 2 vectors are in here. H equaling the span of these 2, right? So this V has a bunch more things in it, but what I'm looking at is just the span of these 2 vectors. So let's verify that this is a subspace. So first off, I can get to the 0 because if I take 0 times the first vector plus 0 times the second vector, I get to the 0 vector. Oops, should have a 0 vector on that. Then it's closed under addition because of my U vector is equal to A and B times the V1 and the V2, and my W vector is a C and D times my 2 vectors. Then when I add them together, I get a linear combination of V1 and V2. That means it's in the span, so that's closed under addition. It's closed under scalar multiplication because if I have this vector U that's inside the set H, then I can take that U and multiply it by C and it stays in the span, and so then it stays in the subspace H.